Welcome to the Deep Dive.
Mm.
Today we're diving straight into generative AI.
Mm-hmm.
You've likely seen its results, right? Maybe some really stunning images or read text that sounds surprisingly human.
Definitely. It's becoming pretty hard to miss.
But what's the real story? What's actually going on behind the scenes? And what can it really do? That's what we want to get into today.
Yeah, absolutely. Put simply, generative AI has this, remarkable ability to create entirely new things. It's not just analysis.
Right. Traditional AI is more about analyzing data that's already there, spotting patterns, making predictions.
Exactly. Generative AI learns from, vast amounts of data, huge data sets, and then uses that learning to produce genuinely novel content.
So things like realistic conversations.
Or compelling stories, original images, even music and videos, all coming from algorithms, essentially.
Okay. And for this deep dive, we've looked at quite a few articles, some research.
Yeah, try to get a broad picture.
To give everyone listening a really clear understanding. What's the core of generative AI? What can it do? And what are the important things to keep in mind?
The goal is really to cut through some of the hype, maybe.
Yeah, exactly. Give you those aha moments. Show how AI can be creative in maybe surprising ways and touch on the implications, the not so obvious stuff, without getting bogged down in, super technical jargon.
And it is fascinating, isn't it, how AI, which we often think of as purely logical, can now kind of tap into something that feels like creativity.
Yeah.
So we'll look at how it learns to generate these new outputs, explore some of the, frankly, surprising ways it's already being used, and also touch on some of the bigger questions, the wider considerations that come with this kind of powerful technology.
Okay, sounds good. Let's unpack the fundamentals then. At its core, generative AI relies on something pretty basic, right? Data. Lots of it.
That's absolutely right. Huge amounts of data are fundamental. These models are trained on these massive data sets.
And they analyze this data.
Yeah, in incredible detail. They learn the underlying patterns, the structures, the relationships within all that information. It's a bit like how a child learns language, maybe, by just hearing countless conversations.
Okay, but it's not just about copying what it's seen, is it? That feels like a key distinction.
Definitely not just copying. The whole point is to generate something new, something original.
But still related.
Yes, exactly. Sharing the characteristics of the data it was trained on. So if you train it on portraits, it should create a new portrait, one that wasn't in the training set but still looks like a plausible portrait.
Got it.
And here's another key insight, I think. The generation process often has this element of, randomness or chance built in. It's probabilistic.
Meaning
if you give the same prompt, the same instruction, to a generative AI model multiple times.
You might get different results each time.
Precisely.
Yeah.
Different, but hopefully equally valid or plausible results. It's not like a calculator where 2 + 2 is always 4. It explores possibilities within the patterns it's learned.
Which is probably part of what makes it feel creative, right? It's not deterministic.
Exactly. That variability is key.
Okay, and we're hearing these terms thrown around a lot. Foundation models, large language models, or LLMs. How do they fit in?
Right. Think of foundation models as these really big, versatile AI systems. They get this initial, very broad training on just a massive amount of general data.
So they learn a bit about everything.
Sort of, yeah. And that broad training means they can then be adapted or fine-tuned for lots of different specific tasks without needing to start from scratch every single time.
And LLMs are a type of foundation model.
Yes, exactly. Large language models are a specific type focused on, understanding and generating human language.
Like text.
Like text, yeah. And the really crucial point here is the scale. The sheer size and the variety of the data used to train these foundation models. And LLMs, that's what unlocks their really impressive capabilities.
So the more data they ingest during training, the better they generally get at generating these new outputs.
Broadly speaking, yes. Scale has been a major driver of progress.
Okay, this is where it gets really interesting for me. How does this generation actually happen? Like, what are the main techniques inside the box?
Yeah, okay. So there are several important architectures, different ways these models are built. Two really prominent ones, especially historically, are variational autoencoders.
VAEs.
VAEs, yeah. And generative adversarial networks, or GANs.
Okay, let's start with VAEs. Sounds a bit technical. What's the core idea?
Okay, so at its heart, a VAE has two main parts, an encoder and a decoder.
Encoder, decoder. Got it.
The encoder takes the input data, let's say it's an image, and it compresses it down into a smaller, more compact representation. We often call this the latent space.
Like a summary or the essence of the image.
Kind of, yeah. But it's a special kind of summary. Then the decoder takes a point from this latent space and tries to reconstruct the original image from that compressed information.
So it compresses, then uncompresses. It's just like zipping a file.
Not quite. And this is the key difference with VAEs. The encoder doesn't just learn one fixed compressed version.
Okay.
Instead, for each feature it's representing in that latent space, it learns a range of possibilities. It learns a probability distribution.
Explain that a bit more. Like, instead of saying, this pixel is blue.
Well, more like, imagine describing a face. Instead of fixing the nose is exactly 3 centimeters long, the VAE learns like the typical range of nose lengths and shapes found in the training data. It learns the mean and the variance, essentially.
Yeah. Okay, so it captures the variability, the essence of noseness, rather than one specific nose.
Precisely. It learns a distribution for each feature. Then when it wants to generate something new, the VAE basically randomly samples a set of feature values from these learned distributions, these ranges, in the latent space.
It picks a plausible nose length, a plausible eye spacing, etc.
Kinda, yeah. It picks a point within those learned probability clouds, and it feeds that combination of sampled features into the decoder.
And the decoder turns that back into an image.
Exactly. The decoder generates a new image, one that shares the characteristics of the original training data because it was built from those learned distributions, but it's usually not an exact copy of any single input image.
That makes sense.
Yeah.
That explains how you could get, say, slightly different versions of a chair design or variations on a theme.
Exactly. VAEs are really good at generating variations. And to make sure this whole process works well, they use a special kind of training objective, a loss function.
Okay.
One part of it pushes the decoder to reconstruct the original input accurately. That's the reconstruction loss.
Makes sense. You want it to learn properly.
But there's another crucial part, often involving something called KL divergence. This part encourages those learned probability distributions in the latent space to be, well, nicely behaved, smooth and continuous.
What does that mean, nicely behaved?
It means you don't want big gaps or weird jumps in the latent space. You want similar concepts to be close together. So if you move just a tiny bit in the latent space, the generated image should change only slightly, in a meaningful way. It ensures the space is well structured for generation.
Okay, so the different ideas flow into each other smoothly.
That's a good way to put it. It helps generate diverse but still coherent outputs.
You also mentioned something called a reparameterization trick. Sounds like some kind of magic.
It's more like a clever mathematical technique because the generation involves that random sampling step.
Yeah.
It makes it tricky to calculate how to adjust the model during training using standard methods like backpropagation. The trick essentially separates the random sampling part from the parts of the model that need to be learned, making the whole optimization process possible.
Okay, so it's a necessary bit of math to make the training work smoothly.
Pretty much, yeah. Makes it trainable.
All right, so VAEs sound pretty useful then. Where do we actually see them being used?
Well, as we said, generating similar but new images, exploring variations, that's a big one.
Right.
They're also used for data compression because that latent space is a compressed representation.
Right.
They can be good at anomaly detection, identifying data points that are really different that fall outside those learned distributions.
Like finding a faulty product on an assembly line.
Potentially, yeah.
Yeah.
Or finding weird network traffic. And also for data imputation, filling in missing parts of data based on the learned patterns.
Interesting.
And historically, VAEs were really significant. They were some of the early deep learning models that could generate quite realistic images and speech. They're still valuable for that ability to balance reconstruction accuracy with generating novel variations.
Okay, that gives a good picture of VAEs. Now, what about the other one you mentioned, GANs, Generative Adversarial Networks? The name itself sounds competitive.
It is. That's the core idea. A GAN involves two neural networks, a generator and a discriminator.
Two networks working together or against each other.
Against each other, hence adversarial. They're trained simultaneously in this competitive game.
Okay, what are their roles in this game?
So the generator's job is to create fake data synthetic images, for example, that look as real as possible. Its goal is basically to fool the discriminator.
And the discriminator.
The discriminator's job is to be the detective. It gets fed both real data from the training set and the fake data produced by the generator.
And it has to figure out which is which.
Exactly. It tries to correctly classify inputs as either real or fake.
So it's like a counterfeiter and a cop constantly trying to outsmart each other.
That's a perfect analogy. The generator gets better at making fakes because the discriminator keeps catching its flaws, and the discriminator gets better at spotting fakes because the generator keeps trying new tricks.
It's a constant arms race, pushing both of them to improve.
Precisely. Through this ongoing competition, this adversarial loss, both networks improve. The generator learns to produce increasingly realistic synthetic data.
Making it harder for the discriminator.
Right. And the discriminator gets better at telling the difference, pushing the generator to improve even further.
So when does this competition end? What's the ideal outcome?
Ideally, you reach a point called equilibrium, where the generator is creating fakes that are so good
Yeah.
that the discriminator is basically just guessing. It can't reliably tell the difference anymore, maybe getting it right only 50% of the time.
Which means the generator has become really, really good at making realistic stuff.
Exactly. That signifies the generator has learned the underlying distribution of the real data very well.
That's a really clever setup.
Yeah.
So where do GANs really shine? What are they particularly good at?
GANs have shown incredible success, particularly in generating highly realistic images. Much of the progress in photorealistic faces, animals, objects, things that look almost like real photographs came from GANs initially.
Wow. Okay.
They're also used for other visual tasks like generating videos from text descriptions, creating synthetic data sets for training other AIs.
Why synthetic data?
Well, sometimes getting enough real-world data is hard or expensive or has privacy issues. So you can train a GAN on the real data you do have and then use it to generate lots more synthetic data that shares the same characteristics to augment your training set.
Clever. What else?
Image completion, or in-painting, filling in missing parts of an image convincingly, even generating 3D models. Their strength is really in achieving that remarkable level of realism, especially in visual and multimedia domains.
But are there downsides?
Yeah, training GANs can be notoriously tricky. They can be unstable, sometimes one network overpowers the other, or they fail to converge properly. It requires careful tuning and often a lot of computational power.
Okay, so VAEs for variations, GANs often for realism, though trickier to train. It feels like the field hasn't stopped there, though. What other key techniques have emerged? The space moves so fast.
You're absolutely right. It's incredibly dynamic. Beyond VAEs and GANs, transformer models have been completely revolutionary,
Right.
especially for language.
Transformers, right. We hear that name a lot with models like GPT.
Exactly. They use this mechanism called self-attention. It allows the model to weigh the importance of different words in an input sequence when processing any given word.
So it understands context better, how words relate to each other, even if they're far apart in a sentence.
Precisely. It gets a much richer understanding of context and relationships. Models like GPT, BERT, Gemini, they're built on this transformer architecture, and they've shown, just incredible abilities in generating coherent, contextually relevant, often very human-sounding text.
Okay, so transformers are huge for text. What else is making waves?
Diffusion models. These are another really powerful approach that have become maybe state-of-the-art for image generation and increasingly video, too.
Diffusion. How do they work? It sounds different again.
It is. The core idea is learning to reverse a process of gradual noising. Imagine starting with a clear image and step by step adding a tiny bit of noise again and again until it's just pure static.
Okay, destroying the image gradually.
Right. A diffusion model learns the reverse process. It learns how to take that static noise and, step by step, remove the noise, guided by perhaps a text prompt, to reconstruct or generate a clean, coherent image.
Wow, that's a fascinating concept. Learning to create by learning to undo noise.
Exactly. And models like DELI 2 and 3, Imagen, and especially Stable Diffusion are prominent examples. They can generate stunningly realistic and creative images from text descriptions.
Stable diffusion is one you hear about a lot, especially in the open source community.
Yes, its availability has spurred a lot of innovation.
Okay, any other major types we should be aware of?
Well, there are others worth mentioning briefly. Autoregressive models are quite fundamental too. They generate data sequentially, step by step.
Like predicting the next word in a sentence.
Exactly. Predicting the next element based on the elements generated so far, very common for text, but also used in audio generation.
Right.
And related to sequential data, you have recurrent neural networks, RNNs, and their more sophisticated cousins, like LSTM's long short-term memory networks.
Ah, yeah, I remember those. They have memory, right?
Yes, they have internal states that act as a kind of memory, allowing them to capture dependencies over time in sequences. So they've been historically important for music generation and text generation too, though transformers have largely taken over for text.
Okay.
Then you have things like flow-based models, which learn exact reversible transformations between a simple distribution and the complex data distribution. And even older methods like Markov chains, which are statistical models for generating sequences based on probabilities of transitioning between states.
That's a great rundown of the engine room, the core techniques. So let's shift gears slightly. How can we categorize the types of generative AI models based on what they actually create? Like by data type.
Yeah, that's a really helpful way to think about it. We can group them by modality. Let's start with probably the most visible type right now, text generation.
Right, things like ChatGPT and other chatbots have really brought this to the forefront.
Absolutely. The goal here is pretty clear. Produce written content that feels natural, like a human wrote it. Good grammar, coherent ideas, appropriate style.
And we already mentioned the key players, transformers.
Exactly. Architectures like the GPT series, GPT-3, GPT-4, Google's Gemini, Meta's Llama, Anthropic's Claude. These are all prominent examples, primarily based on transformers. They're trained on just unbelievable amounts of text data from the internet and books.
Billions, trillions of words.
Easily. And that scale allows them to learn the nuances of language, context, and different writing styles.
And the applications are just exploding, aren't they?
Oh, completely. Content creation is a big one. Articles, blog posts, marketing copy, emails.
Summarization, too. Taking long documents and boiling them down.
Yes, summarization, translation between languages, powering those conversational chatbots we mentioned.
Customer service bots.
Yeah, and more sophisticated virtual assistants, and even code generation writing computer code in various programming languages. The progress driven by these large language models has been truly transformative.
Okay, moving from text to images. Image generation. We touched on some techniques already.
Right. The focus here is creating new visual content. This could be anything from trying to make photorealistic images that look like photographs
to more artistic or stylized images.
Exactly. And the key models and techniques we discussed come into play here. GANs, especially variants like Stylian for high-quality faces, VAEs for variations, and increasingly diffusion models like DALL-E, Midjourney, Stable Diffusion. Even transformers are being adapted for image tasks now.
And they learn from huge data sets of images, I assume.
Massive image data sets, often paired with text descriptions, which is crucial for the text-to-image model.
So what are the main things people are doing with these?
Text-to-image generation is probably the most well-known application right now. You type a description, you get an image.
Yeah, it feels like magic sometimes.
It really does.
Yeah.
But also image editing tasks like in-painting, filling in missing parts, out-painting, extending an image, style transfer, applying the style of one image to another, generating synthetic image data like we talked about with GANs for training computer vision models, and of course, enabling new forms of digital art and creative expression.
And you mentioned diffusion models are particularly strong here.
Yes, they've really pushed the boundaries in terms of image quality, realism, and coherence, especially for generating complex scenes from detailed text prompts.
Okay, text, images. What about sound? Music generation. This feels like a really creative frontier.
It absolutely is. The goal here is composing original musical pieces, generating sound effects, maybe transforming existing audio.
Changing the genre of a song, maybe.
Exactly, things like that. And various techniques are being applied. We mentioned RNNs, like Google's Magenta project used Melody RNN. Transformers are also used, like Music Transformer or OpenAI's MuseNet.
GANs and VAEs, too.
Yes, GANs and VAEs have been explored for music, and now diffusion models are making a big impact here as well, with models like Google's MusicalM, Meta's MusicGen, and Stability AI's Stable Audio.
So similar trends as in image generation. What are the applications?
Generating royalty-free background music for videos or games is a practical one.
Okay.
Transforming music, like we said, changing styles or instruments, creating custom sound effects, and potentially assisting human composers, helping them brainstorm ideas, generate variations, or break creative blocks.
The progress seems really rapid here, too. Models generating music in specific styles, even mimicking artists.
Yeah, the ability to emulate styles is getting quite sophisticated, which of course also raises interesting questions about authorship and copyright.
Definitely. Okay, beyond text, image, and music, what other types of generative AI are bubbling up?
Well, code generation is becoming huge. Models like OpenAI's Codex, which powered early versions of GitHub Copilot, and DeepMind's AlphaCode. They can understand natural language descriptions or partial code and generate working code snippets or even entire functions.
That must be a massive help for software developers.
Potentially, yes. Increasing productivity, automating boilerplate code, helping debug. It's a very active area.
What else? Video?
Video generation is advancing incredibly fast. Just a short while ago, generating even short, coherent video clips from text seemed futuristic. Now models like OpenAI's Sora, Runway's Gen 2, Google's Lumiere, they're demonstrating remarkable capabilities. Still early days in some ways, but the progress is startling.
Generating short movies from text prompts.
Essentially, yeah. Or animating still images. And then there's 3D modeling. Still more in the research phase compared to images or text, but models are being developed that can generate 3D objects from text descriptions or 2D images.
Which could be huge for gaming, virtual reality design.
Exactly. Lots of potential impact there.
It really feels like there's a generative model being developed for almost every kind of data or creative output now.
That's definitely the direction things are heading. And, it's worth mentioning for listeners who want a really structured overview, the source material we looked at often includes tables that lay this out nicely.
Ah, okay. How so?
They typically categorize by data type, text, image, music, code, video, 3D, and then list the main techniques used for each, give specific model examples, outline the common applications, and, importantly, discuss the strengths and current limitations of each type. It's a great way to get a quick, comprehensive snapshot.
That's useful. A good reference point. Okay, so we've got a handle on the what and the how. Now let's broaden out again and look at the where. Where is all this technology actually being used? Across different industries, it feels like it's popping up everywhere.
It really is spreading rapidly. We've touched on art and creative content quite a bit, generating digital art, music, writing. It's kind of democratizing creation in some ways.
Letting more people create things.
Yeah, potentially lowering the barrier to entry. But also leading to a huge increase in the volume of content being produced, which raises its own questions about value and authenticity.
Sure. What about, say, software development? We mentioned code generation.
Yeah, that's a big one. Boosting developer productivity is the main driver. Generating code, suggesting auto-completions, helping find bugs, even explaining complex pieces of existing code in natural language.
Automating the grunt work, maybe.
Exactly. Freeing up developers for higher-level design and problem-solving.
And in the sciences, is it making an impact there?
Definitely. It's becoming a really valuable tool for accelerating scientific discovery in fields like drug development and material science.
How so?
Well, models can help design novel drug candidates or predict the properties of new materials, potentially speeding up the lengthy R&D process significantly.
Wow.
Researchers are also using it to analyze incredibly complex data sets from genomics or climate modeling, for instance. And like we mentioned, generating synthetic data when real-world experimental data is scarce or difficult to obtain.
It really does seem incredibly versatile. What about other, maybe more traditional industries?
Oh yeah, it's making inroads everywhere. In marketing, it's used for creating personalized ad copy, email campaigns, even generating images for campaigns, chatbots for customer engagement too.
Yeah, healthcare.
Analyzing medical images like X-rays or MRIs to help detect anomalies, assisting with diagnosis, even potentially helping design personalized treatment plans based on patient data. Still requires human oversight, of course, but the potential is there.
Finance.
Fraud detection is a big one, identifying unusual transaction patterns. Also, risk assessment, algorithmic trading, and again, customer service chatbots.
It seems like customer service is a common thread.
It is. Telecoms use it for that too, and also for things like network optimization. Gaming is another huge area, procedural generation of game levels, characters, narratives, textures.
Making game worlds richer and more dynamic.
Potentially, yeah. And even product design, using generative models to rapidly create and iterate on design options for physical products, optimizing them for certain criteria.
So across the board, it seems like common themes are personalization, automation, and efficiency gains.
Absolutely. Those are some of the key drivers for adoption in almost every sector you look at.
So let's crystallize those advantages. What are the main benefits that are making businesses and individuals adopt generative AI so quickly?
I think increased efficiency and productivity is probably number one for many businesses.
How does that manifest?
Automating the creation of content, whether it's text, code, or images, handling routine, repetitive tasks, it just saves a huge amount of time and effort.
Freeing up people for other things.
Exactly. Boosting overall productivity by letting humans focus on more complex, strategic, or creative work. Streamlining workflows.
Okay. Efficiency. What else?
Fostering innovation and creativity is another big one, I think.
We talked about generating new ideas.
Right. It can act as a sort of brainstorming partner, generating diverse options quickly, helping artists, designers, writers, scientists explore avenues they might not have thought of otherwise. Pushing creative boundaries, maybe?
So not replacing creativity, but augmenting it.
That's often the goal, yeah. Augmenting human capabilities.
And personalization came up a lot.
Yes. The ability to tailor content, products, or experiences based on individual user data or preferences, that's incredibly valuable in areas like marketing, e-commerce, entertainment.
To increase engagement.
Yeah. Enhance user engagement and satisfaction by making things feel more relevant.
Okay. And I imagine there's a cost angle, too.
Definitely. Cost reduction and scalability. By automating tasks that previously required significant human effort,
You can reduce labor costs.
potentially, or reallocate resources. And generative AI systems can often produce content or analysis at a scale and speed that would be impossible for human teams alone. This makes it cost-effective to scale up operations or optimization efforts.
So efficiency, innovation, personalization, cost savings,
Yeah.
those are pretty compelling advantages.
Yeah.
But it can't all be perfect, right? What about the limitations, the challenges, maybe even the risks?
No, absolutely not perfect. There are significant limitations still. One major issue is accuracy, or rather, inaccuracy. These models can hallucinate.
Hallucinate, you mean they just make things up?
Essentially, yes. They can generate information that sounds plausible but is factually incorrect or nonsensical or doesn't logically follow from the prompt. They don't have true understanding or access to real-time facts in the way a human does.
So you can't always trust the output.
Definitely not blindly. Lack of control is another issue. Sometimes it's hard to get the model to generate exactly what you want, especially for complex or nuanced requests.
And bias is a big concern, isn't it?
A huge concern, since they learn from vast data sets, which inevitably contain biases present in society.
They learn those biases too.
Yes, and they can even amplify them, generating stereotypical or unfair content. This requires very careful dataset curation and model evaluation.
What else?
They can struggle with complex reasoning or tasks requiring deep common sense. They have high computational demands. Training these huge models takes enormous resources, and their performance is heavily dependent on the quality and scope of the training data.
So human oversight is still crucial.
Absolutely critical. For fact-checking, for bias detection, for ensuring the output is appropriate and useful.
Okay, those are limitations. What about potential risks? Things that could go wrong?
There are definitely risks. The potential for misuse is significant. Think deepfakes.
Generating fake videos or audio of real people.
Exactly.
Or-
Which can be used for scams, political manipulation, harassment. Generating convincing misinformation or propaganda at scale is another major worry. Harmful content generation.
Yeah, that's scary stuff.
Intellectual property and copyright issues are also a minefield.
Also,
Questions around the ownership of AI-generated content, and crucially, the legality of using copyrighted material in the training data without permission. Lots of lawsuits and debate around that right now.
right.
Job displacement is another concern, the potential for AI to automate tasks currently done by humans, and privacy and security risks, especially if models are trained on or interact with sensitive personal data.
So there are broader ethical dilemmas and a real need for guidelines and maybe regulation.
Absolutely. Finding the right balance is key.
Okay, so acknowledging those challenges and risks, looking ahead, what are some of the future trends? Where is this technology likely heading?
Well, we can definitely expect continued advancements in the model architectures themselves, making them more sophisticated, more efficient.
Instead of performance?
Yeah, aiming for greater coherence, accuracy, and maybe even more nuanced creativity. Models with larger context windows, meaning they can remember and process much longer sequences of information, are becoming more common, which helps with understanding complex topics or conversations. Enhanced reasoning abilities are also a big focus of research.
What about how we interact with them? You mentioned multimodality earlier.
Right, that's a huge trend. Moving beyond just text or just images towards AI that can seamlessly process, understand, and generate content across multiple modalities, text, image, audio, video, maybe even others.
More like how humans communicate.
Exactly. Understanding an image and describing it in text, or generating a video based on a spoken command and a musical style prompt. That's the direction.
And more interaction.
Yeah, enhanced interactivity too, giving users more fine-grained control over the generation process, maybe through more intuitive interfaces, allowing for real-time adjustments, feedback loops, making it feel more like a collaborative process between the human and the AI.
And what about the underlying tech? More computing power, more data.
That will continue to be a major driver. Increased computational power allows for training even larger, more complex models, which generally leads to significant performance improvements, more realistic, coherent, creative outputs.
But does that mean only big companies can play?
Well, while training the biggest models is expensive, there's also a trend towards democratization. More powerful models are becoming accessible through cloud platforms, and the open source movement is really important here.
Making models like Stable Diffusion available for anyone.
Exactly. Releasing powerful models and tools openly fuels widespread experimentation and innovation beyond just a few large labs. So increased power and data will lead to better models, but hopefully also broader access.
That brings us nicely to the ethical side again. These future advancements make the ethical considerations even more important, don't they?
Absolutely critical. As the models get more powerful and pervasive, the ethical challenges intensify.
What are the key pillars we need to focus on?
Transparency, accountability, and fairness are huge. We need to understand as much as possible how these models work and make decisions. That's transparency.
The black box problem.
Right. We need mechanisms to determine who is responsible when things go wrong. That's accountability. And we need to actively work to ensure these systems don't perpetuate or amplify biases, leading to unfair or discriminatory outcomes. That's fairness. Building trust relies heavily on these three.
And we touched on privacy, security, and intellectual property, too.
Yes. Protecting personal data used in training or interaction is paramount. Robust security measures are needed to prevent misuse. And navigating the complex IP issues, fair use of training data, ownership of generated content requires clear guidelines and probably new legal frameworks.
Which leads to regulation. Is that inevitable?
It seems increasingly likely we'll see more regulatory frameworks emerging globally. The challenge is finding the right balance.
Encouraging innovation while safeguarding against harms.
Exactly. Preventing the spread of misinformation, mitigating bias, protecting privacy without stifling the positive potential of the technology. It will require careful thought and collaboration between researchers, developers, policymakers, and the public. Developing industry standards and best practices will also be crucial.
It's a complex balancing act.
For sure.
Okay, so to kind of wrap up our deep dive today, we've covered a lot of ground. Generative AI, this incredible power to create novel content.
Driven by techniques like VAEs, GNs, transformers, diffusion models.
All trained on massive data sets to learn underlying patterns.
Yeah.
And its applications are already incredibly diverse across almost every industry imaginable.
Offering real benefits in terms of efficiency, productivity, and fostering innovation and creativity.
But crucially, it comes with limitations, hallucinations, bias, control issues, and significant risks, like misuse and IP challenges.
Highlighting the need for caution and ongoing research.
And the future looks set for even more sophisticated models, this move towards multimodality, better interaction.
And hopefully wider, more accessible innovation alongside those critical ethical considerations around fairness, transparency, and accountability.
It's a field moving at lightning speed with enormous potential and significant responsibility attached.
Couldn't agree more. It's definitely one of the most dynamic and impactful areas of technology right now.
So on that note, maybe a final thought for everyone listening. As we've explored all this, consider the balance, the incredible potential of generative AI to create, to discover, to personalize, versus the responsibility we all share in guiding its development and use ethically.
It's like a crucial tension.
Yeah. So maybe think about this. Which application of generative AI do you find most transformative? Or perhaps most concerning, or just intriguing, and why? It's definitely something worth mulling over as this technology continues to reshape things around us. Thanks for joining us on this deep dive.